I think I am live now. Can anyone confirm if audio and everything is fine? Like, I will wait for a minute or more and then I will get started with discussing the problem. I was able to solve all the problems, so I would be discussing solution of all the problems. And like probably I know there is a code forces round just after it. Like I will probably first focus on discussing all the problems, and then if I have time, I will solve code forces contest and solve the problems over there. And like probably those who want to participate in code forces round might participate in code forces round, and then there would like their stream would be available, so like they can look at it later. So like can anyone confirm if audio and everything is fine before we get started? And like how was your contest? Okay, someone is asking, I hope F is some linear algebra trick like Gaussian elimination because DP seems too tight. Like I would say my solution was along the lines of DP only. Like the idea is like SOS, like if you know somehow subset DP, like what I did was modified a bit over there and got away with it. Okay, yeah, thanks for the 4K subs. Like I recently hit that goal over there. And like I think I will get started now. First problem is zero sum game. You are given n people labeled 1 to n. You have played several one-on-one games without draws. Initially, each person started with 0 points. In each game, the winner's score increased by 1 and loser's score decreases by 1. Scores can become negative. Determine the final score of person n. If the final score of I person is AI, it can be shown that the final score of n person is uniquely determined regardless of the sequence of it. Here, like the problem statement is a hint over there. Like if you notice, like the sum of score of all the players will always be 0, because whenever someone's score increases by 1, there is someone else whose score decreases by 1 as well. So the idea is like we will probably take sum of all the players score we know, and then we will multiply it with by -1 and print it. So for example, 1 -1 -2, like their sum is -2, so like n player score is 2, so that like if you take sum of this and this, overall the sum still remains 0. If everyone has 0 score, then this player also has a 0 score because the sum remains same over here. And here, like if this everyone's score is 10, 20, 30, 40, 50, then like the other player must have -150. So that sum of everyone is 0 over here. And essentially that was the idea. And like the problem statement name was really a hint over there. And like this is my submission. Like I read an integers, took a sum of all of them and printed minus sum at the last. Any questions on this one before we move to the next problem? Okay, moving to the next problem. It says commencement. A string S consists of lowercase English letters is a good string if and only if it satisfies following property for all integers not less than 1. Like not less than 1 literally means all the positive integers, basically everything which is greater than equal to 1. There are exactly 0 or exactly 2 different letters that appear exactly I times in S. Determine, given a string S, determine if it's a good string or not. So like the idea is like for each letter we can count how many times it appears. Like the idea is like first, one second. Yeah, okay, yeah. So the idea is like first count how many times each character appears. Then like for each frequency character, we can again maintain a frequency array for them, and then at last for each integer check they appears only two times, and like pretty much that was the idea. And like here the idea would be like first we count for each character how many times it appears, then we'll take like how many times that appear as a different array and see like each number in it either appears two times or zero times. So like first a frequency array of all the characters of string, that would be for each character in S frequency S plus plus. Then I have maintained a vector, like you can also use a map or anything over here. Then like for each character's frequency, like how many times it appears, add plus one to this frequency two array. And at last iterate on this frequency two array, and every number should either be zero or two. And if it's not equal to zero or two, return FL as false. And at last check if FL is yes. Like if it's yes, print yes, otherwise no. And pretty much that was the idea for this problem. Like any questions on this one? Like it was more on the implementation side rather than anything else. And like if there are no questions, I will move to the next problem. Like first find frequency of each character, like how many how many times each character appears, and then on that side like again count for each number how many times it appears. Or like a brute force way can be like you can start for each I from 1 to 100, check if it appears two times or not. So if there are no questions, I will move to the next problem then. Airport code. It says a string T of length 3 consists of uppercase English letters is an airport code if S of lowercase English airport code for a string S of lowercase English letters if and only if T can be derived from S by the following method. Please repeat the idea of the implementation. Okay. Okay, the idea is like first I count how many times each character appears. Like this is in my frequency array. Then for each I equal to 1. Like given string has length at max 100. So like no character can appear more than 100 times. Now for each I iterate and check like how many characters appears I times in it, which is in my variable counter. And if count I is not equal to 2, I should return no. And if it does not exist anywhere here, then all the characters appear either 0 or 1 time. And I should print yes over there. And like this is the idea. And why 100? Like I know that. So like if n is the length of string, then no character can appear more than n times. So like everything apart from this range would be like 0 times over there. And like this is the idea. And like this was the idea for this problem. I will move to problem C then. Problem C says airport code. A string T of length 3 consists of uppercase English letters is an airport code for a string S of lowercase English letters T if and only if T can be derived from. S by one of the following methods. Take a subsequence of length 3 from S, not necessary continuous, and convert it to uppercase letters to form T. Or take a subsequence of length 2 from S, not necessary continuous, convert it to uppercase English letters and append X to the end to form T. Given S and T, determine T is an airport code for S. And it's even like T is uppercase string of length 3 and S is uppercase string of length 3 to 1E5. So like there are multiple ways to do it. Like first thing we should do is like if the last character of T is X, remove it. Now T either contains 2 or 3 characters. And then convert like first step. Second step, convert T to lowercase English letters. And third step is check if T is subsequence of S. And like this, to do like check subsequence, like we can use the greedy idea. And like I think like it has appeared a lot of times. Like to check if now the T is subsequence of S or not, we can use greedy. Like we maintain two variables, I and J. Like basically we iterate on all the characters of X. And we maintain a variable like IDX, TIDX, which starts from 0, like the next character that should match here. And if current character equal to T of TIDX, we increase our pointer again and we keep doing it. So like basically the idea is like, let me take a sample example to make things a bit clear. Like let's pick this character, A loss. Like I have added A extra to it. Angelus, this is S. My T is LAX. So the first thing I did is like because X is the last character, I just remove it. And then I also convert all the characters to the small case letters here, which would be LA. Now what I do is like this is my S and this is my modified T, LA. I maintain a pointer here. Like first the pointer would be on the first character. I iterate on all the characters here. Like the first character is not equal to my current pointer. So I will not do anything for the current pointer and I will move to the next character. And now the next character, there is a match with my current pointer. So I will move my current pointer a bit side over here. And then I will move to the next character here. Again, like this character matches. So like I will move my current pointer a bit forward here. And so on. And at last I should check like if I have reached the end of the string or not. Like let me take some better example. Let's say this is my S and like this is the string which I want to check whether matches or not. I first maintain my current pointer here. I start from it. A is not equal to C, I skip it. B is not equal to C, I skip it again. Like C is equal to C here. So I move my current pointer on D a bit forward. Now I check like is D equal to my current pointer? No. Is E equal to my current pointer? No. Is F equal to my current pointer? Yes. So now I have a match here. And I move my this pointer a bit forward. Then I check is A equal to my current pointer? No. Is B equal to my current pointer? Yes. So like I move now this pointer a bit forward. And once I have reached the end of this modified string, I can say that like CFB is the substring of the given string, and I should print yes. And if I do not move to the end of the by this time, I should print no. And like this is generally a greedy idea to check if T is substring of given string S. And like that's what we should also do over here. I will move to the implementation part now. Like any questions on this one, like why does it work, or like what is the idea? Like I have converted all the string to a lowercase letter. If my current string is equal to the current character, I increase the pointer here. And like this would be the idea. Yes, after all iterations, J should be equal to, it should be equal to T dot size, because we are checking T is a substring of S or not. And yeah, like this is the algorithm for this problem. Any questions on this one before we move to the next problem? Okay, B got an issue. Okay, can you tell like DBG function is mostly used to log characters on the terminal. Like it generally helps in like debugging things if possible. Like you see, like I have a library method which prints all the values, but if it's online, like it just replaces all DBG with 42. So nothing happens when I submit it on the online net. So like here, like there is a warning, like you can see like has defined DBG. So DBG 42 is doing nothing here, has no effect. So the main idea is to print whatever value I want when something is off over there. And like when it's submitted, like DBG is equivalent to which statement which does nothing. Okay, I will move to problem D then. Problem D says divide interval. Like there is a long story. Like for non-negative integers L and R, let S L to R denotes all the numbers from L to R minus 1. Like and like it says we are given integers L to R and we should divide. Okay, let me read it correctly. For a non-negative integers L to R, SLR denotes the sequence L to R minus 1 formed by arranging letters from L to R minus 1 in order. Furthermore, a sequence is called a good sequence if and only if it can be represented as S 2 to the power I into J into 2 to the power I into J plus 1 using non-negative integers I and J. You are given non-negative integers L and R, divide the subsequence S L to R into the fewer number of good subsequences and print that number of subsequence and the divisor. More formally, find the minimum positive integer m for which there is a sequence of pairs of non-negative integers L1, R1, L2, R2, Lm, Rm that satisfies the following and print L1, R1, L2, R1, so on. Like L is equal to L1 and it's increasing, and R1 is equal to L2 and so on. And like Rm is equal to R and all the subsequences are good subsequences. It can be shown that there is only one division that minimizes m. Let's keep the story short. And like probably let's look at the sample to understand what the problem statement is asking us to do. Like basically it's saying that as L to R denotes consecutive integers from L plus 1 up to R minus 1. And it says now you have to divide into some continuous segments of the original sequence. Like let me just take a sample first. 3 to 19. Like let's say like this is S1 to 19. Now we have to divide it into such sequences such that the highest power of 2 is almost same over here. Like for example, like 3 would be the one. Like 3 to 4 becomes like 3 into 2 to the power 0 and 4 into 2 to the power 0. So like this would be the first subsequence. Now like the idea to do is like we can probably look at the, like now we need like 4 to 7 as the next subsequence. Like 4 can also be written as 1 into 2 to the power 2, and 8 can be written as 2 into 2 to the power 2. So like all the numbers from 4 to 7. Next we need would be like 8 to 15. Here like you can also write 8 as 1 into 2 to the power 3, and you can write 16 as 2 into 2 to the power 3. So you can see like the power of 2 here is same, and the number before it increases by 1. And you can also see like there are different ways to write each number. We can also write 8 as 2 into 2 to the power 2, and 8 as also 1 into 2 to the power 3. And next it says like 16 and 17 should be taken, because like 18 we can write it as 9 into 2, and we can write 16 as 8 into 2. And like at last we can again take 18 as a subsequence, because 18 can be written as 18 into 2 to the power 0, and like 19 would be 19 into 2 to the power 0, and so on, something like that. Like probably any questions on like what the problem statement is asking us to do before we try to solve, like how to solve this problem? Okay, so now like let's look at all the numbers, like how, let's see how does all the good subsequences of 2 to the power looks like. Like first we can say like all the numbers from, we can write all the numbers from 0 to 31. Like it's a good sequence, because like 0 to 31 is 0 into 30, 0 can be written as 0 into 2 to the power 5, and 32 can be written as 1 into 2 to the power 5, right? I am not yet decided which power to do. Like the next critical idea is like you can, like if you take the middle element of this sequence, then you can split these sequences into two different sequences as well. Like 0 to 15 and 16 to 31 is also a good sequence. It can be written as 0 into 2 to the power 4, and 16 can be written as 1 into 2 to the power 4, and 32 can be written as 2 into 2 to the power 4. And now if I split both the sequences again, like I can split it into exactly two more sequences. 0 to 7 1, and 8 to 15 another, and 16 to 23 another sequence, and 24 to 32 another sequence, 24 to 31. And like if you see like 0 can be written as 0 into 2 to the power 3, 8 can be written as 1 into 2 to the power 3, 16 can be written as 2 into 2 to the power 3, 24 can be written as 3 into 2 to the power 3, and 32 can be written as 4 into 2 to the power 3, and so on. So like if you see like we have original sequence from 0 to 31, we can divide it into two more sequences, 0 to 15 and 16 to 31. And now these sequences can be further divided into 0 to 7 and 8 to 15, 16 to 23 and 24 to 31. Now you can again divide 0 to 7 into 0 to 3 and 4 to 7, 8 to 11 and 12 to 15. Like, does this diagram looks familiar to you? 16 to 19, 20 to 23, 24 to 27 and 28 to 31. And like I can divide it into more layers. Like, does this diagram looks familiar to you? One question. Like, how does segment tree of numbers from 0 to 31 looks like? And if you see like the nodes which have been it asking us to do is exactly the nodes which would be from L to R we will hit in the segment tree. So for example, if you need 8 to 23, the nodes you would be picking up in segment tree would be like these. Or let's say like we need numbers from 4 to 27. Then if you look at the segment tree, the nodes we would be taking here is 4 to 7, 8 to 15, 16 to 23 and 24 to 27. And like this is in fact the minimum division required over here. Okay, like what is segment tree? Like I would probably give it some examples here. Like I think like it is the data structure which is most commonly used, and like it would be great like if you can probably look at some diagrams over there. Like I would end up sending some problems for the segment tree. Like I would say like segment tree is the first data structure which probably if you are starting out you should try to solve it. So like for, probably if someone does not know segment tree, like I will end up giving some problems for the segment tree, and I think that's the best way to learn it. Like is there a segment tree? Yes, this is the one. Okay, is there a way to prove minimum divisions? Is there a way to prove that this will give minimum divisions? Let me think about it. I think like this is definitely minimum, but let me see if I can prove it. Okay, like how do I prove it? Like the main idea is like can I pair numbers together or once? Hmm, like I would, I'm not really sure like how would explicitly solve it, but like I'm not really sure right now. Like the one way to do it would be like let's say if we start from L. Hmm, like we can start from L to R first, and if L is even, then we can probably add +1 to it, and if R is odd, we can also add +1 to it and divide it by 2 and probably keep going. Like probably the idea can be like if we need numbers from like what was the example I took? If we take numbers from 3 to 27, like the possible way can be like we like what is the smallest or the largest set we can make from 3? Like 3 can be written as 3 into 2 to the power 0. So like 3, if 3 is in a set, like the set must be 3 into 2 to the 3 into 2 to the power 0 and 4 into 2 to the power 1. 4 into 2 to the power 0, right? So now we can first form a set for 3 to 4, 1. And then we can remove 3 from here. And we can recursively solve for 4 to 27. And like we can keep taking maximum power of 2 at each point of time. Now like for 4, like the choices we have maximum power of 2 we can take over here right now is like 1 into 2 to the power 2 and 2 into 2 to the power 2. And like in fact it would be possible. So like we take 4 to 7 as the current segment, and now we try to solve for 8 to 27. 8 to 27 will again end up giving us like 8 to 15 as one segment, and like the remaining problem would be 16 to 27. And now you can notice that 16 to 32 is not a valid segment. So like now first we write 16 as 1 into 2 to the power 4. So like it will give us 16 to 32, not the required segment we need. Now we can also write it as 2 into 2 to the power 3, which will give us 16 to 24. So like 24 is inclusive. So that our next range can be 16 to 23, and we recursively solve for 24 to 27, and like that can be the other way to it. And like this would be, I would say, a greedy idea. And like I'm not really sure like how do I explicitly prove it. Like the way I do see, like it would be the maximum one. But let me think about it for a minute. Like generally I am weak at when it comes to proving things there. Like one critical property over here is like either two segments have the same parent power or not. Like the idea is like find the longest segment which the left segment can be a part of it, and then solve it again over there. Like that can be the other idea. Like probably the way to solve it was like once we figured out like the segment tree idea. Coming back to the solution, my idea was like I would assume that I have a segment tree which goes from 2 to the power 61. 61 is inclusive. And I also have L to R as the given range. Now in the segment tree, we generally have ID, L and R. If L and R are completely in this range, I add like this segment and exit there. Otherwise, I find the midpoint. Then I recursively solve for L to mid and mid plus 1 to R. And when I am done with all the segments, I keep a track of all the points, all the segments which I have visited, and I sorted them and printed them. And like that was essentially the idea I had. And by the way, editorial is there, and I think like the official editorial will have a proof for it. Okay, it pretty much does what I did, but with no proof yet. So yeah. Like the other part would be a bit too complicated, but the idea was like I maintain like all the ranges L to R because R is not included. I subtracted R by -1, and like the segment tree idea nodes L to R which are there, and I start with assuming the complete tree of 0 to 2 to the power 61 minus 1. Now if I am out, like if my current number is outside the range which I need, return. If current range is completely inside the numbers I need, add that as a range and return. Otherwise, find the midpoint and recursively solve for the left subtree of the segment tree and right subtree of the segment tree L to M plus 1 to R. And at last print all the nodes which I have visited and all the ranges that they have visited. And like this was the implementation I had. Any questions on this one? Like probably I would say like for the like the way this definition was written, and like I did solve similar problems before, so I knew like segment tree would definitely work here. Or wait, in fact, like I see, like I think I may have a counter test case with me over here. Like this was problem D, right? Like let me think about it. Like, I think I have a corner test case for the segment tree. Like segment tree should not, like my idea should fail for this problem. Okay, no, it's working. 16 to 24 is working. Okay, yeah, no, look, segment tree looks fine to me. So like the other greedy idea can be like you can try to make L and R as the highest power of 2 over here. Like the other way to do it can be like we start with L2R and we also maintain P2, which is initially 1. So at present, like every number L and R both are divisible by 2. Now we want to make it divisible by, like next power would be like 2 to the power 1. So like we should make L and R the powers of 2 here. So if L is odd, we add one range from L to L plus 1 and we change L to L plus 1. So in that case, it would be even number. Similarly, if R is even, it's fine. If R is odd, like we subtract range like from like R minus 1 to R, we take one range and we subtract 1 from it to make it R minus 1. Now both the numbers would be divisible by 2. And now we try to make it divisible by 4. So if the new L dash and R dash are already divisible by 4, that's fine. If they are not divisible by 4, we can take a segment of length 2 from L and segment of length 2 from R from the end. We can push these segments here and then we can, so that like L double dash and R double dash are divisible by 4. And we do it as long as L is not equal to R. And like that can be the other idea to solve this problem. And like now you can probably see like why this, like not the segmentary one, the other idea would work. So like you can see like for each power I am taking at max 2 number. Like this can be other algorithm to solve the same problem. Mhm. Like I'm just trying it out. Mhm. Okay, 3 to 5. Like I need 3 to 4 here. Hmm. Yeah, like let's just move to the next problem instead of debugging it. Okay, problem E, weighted tic-tac-toe. There is a 3 cross 3 grid. Let ij denote the cell at the ith row from the top and jth column from the bottom left. Cell ij contains an integer aij. It is guaranteed that sum of all the numbers is odd. Additionally, all the cells are initially painted white. Takashi and Oki will play a game using this grid. Takashi goes first and they take turns performing the following operations. Choose a cell ij that is still painted white. It can be shown that such a cell always exists at the time of operation. The player performing the operation scores aij point, and then if the player is Takashi, he paints the cell red. If the player is Oki, he paints the cell blue. After each operation, the following checks are made. Check if there is a consecutive cell painted the same color red or blue in any row, column, diagonal. If such a cell exists, the game ends immediately and the player whose color forms the sequence wins. Check if there is a white cell left. If no white cells remain, the game ends and the player with the highest total score wins. It can be shown that the game will always end after finite number of moves. Either Takashi or Oki will win. Determine which player wins if both the player play optimally. Like it is like the idea, like I would say, like it's a game theory idea. Like we have a state of board, and whoever player's turn it is, like he can try to paint all the cells over there and see like if like for each coloring of board we know like who will win if anyone goes forward. Then we can use like the minimax algorithm to find like whoever wins the final game over here. Like the idea is we have this board, and let's say like pink and blue are the colors painted there. In this state, like for each state of board we can know like which player's turn would be next. In this case, the next color painted should be pink, and like who can possibly win it. The way to do it would be like we can first paint pink here and try to solve like who can be the winner. If pink wins, then pink should play here only. But if pink does not win by painting here, then pink should try painting here. And then see like who would win if the game continues from here. If the answer is pink now, then we can play pink here. Otherwise, we should not play pink, and like we can try all the possible cells here. And if after we have tried all the places and like no one really wins over here, then the idea would like blue will win no matter how the pink plays over here. So the winner of this board would be blue. And like this is probably I would say like the game theory idea. Like the idea is like we have some set of board with some colors originally painted and we know whose turn it is. The current player can try painting all the cells one by one and see like who would win if the game continues from here. If in any game like the current player wins, then he can play at that point only. And if no matter how he plays, the other player wins, then we can definitely say the other player would win no matter how the game continues for them. And like that would be the idea. So like it's the problem E, right? So I have assigned as a vector, which is initially 0. 0 means nothing is painted. 1 means like the player 1 has painted it. and 2 means like the next player has painted it. So now I have a recursive function and I also have an assigned variable like which says like state of board at each point of time. So if I have already computed the data for my current set of assignment, I simply return whoever won that game. Otherwise, I check the current board to see like if it's the in the terminal state. The way to do it would be like if 3 consecutive cells have been painted, then I assign that player as the winner. And if no white cell remains, I check the total score. Right, yes, that's the correct. So we brute force all possible ways from current move, and if we lose in all of them, then like we will definitely lose, and otherwise the other player win. So instead of Oki or Takashi, I would say like the current player whose turn it is, he will try all the moves. If he loses in all of them, then there is no way he can win with that configuration. And if there is one way, then like that current player will definitely win by playing in that turn. So like I recursively saw like I simply wrote 3 minus 1 to change 1 to 2 or 2 to 3 otherwise. And like, so I have a recursive function which finds the initial state when no color has been assigned. Like we do need to memorize state, otherwise there would be n factorial ways and like n factorial might not get TLE. So like memorization might not be required, but I in fact did it because now I know that the number of state can be 3 to the power n only, not more than n. If I do not memorize, the number of state would be, sorry, if I memorize, number of state would be 3 to the power 9. If I don't memorize, number of times I would go recursively would be 9 factorial. And it might not. And then I have a check function which takes current state of board and see who wins. So if it first check like if each row has the same color, then whoever has that color wins. If each column has the same color, whoever has that color wins. If a diagonal has same color, then whoever has painted the diagonal wins. If the other diagonal has the same color, whoever has that diagonal wins. And if no matches happen, then I iterate on all the colors. If there is an unpainted cell, then the winner is not decided yet. Otherwise, I take the difference of score of both the players, and like if score is positive, first player is wins, otherwise second player wins. And like that was the main idea for this problem. And I start with unpainted board, first player as a turn, and like I check the final result if I try all the possible ways. If result is 1, Takashi win. If result is 2, okay wins, and like that was the idea I had. Mhm. And let's just see if memorization was required or not. Like 9 factorial might get TLE, might not get TLE. Like the one with memorization definitely gets an AC. And the one without memorization also in fact gets an AC because 9 factorial is small enough. So like this was the idea for this problem. Any questions on this one before we move to problem F? Okay, I think the code forces round started, like that's why some people might want to do it, but I will finish the explanation of FNG before ending the stream. So if someone wants to do code forces round, they can come back to the stream later. Okay, problem F says subsequence LCM. You are given a sequence of positive integers a1 to an of length n and a positive integer m. Find the number modulo this of non-empty, non-necessary continuous subsequences of A, such that the least common multiple of all the elements is a subsequence in M. Of the subsequence is M. Two subsequences are distinguished if they are taken from different positions in the sequence. even if they coincide as the sequences. Also, the LCM of the sequence of single element is that element itself. Some examples are given, like for example, we have number 2, 3, 4, 6, and there are 5 sequences which has LCM 6. That are 2, 3, 2, 3, 6, 2, 6, 3, 6, 6, and so on. Like I think the problem statement is clear, but like how to solve it was a bit difficult part. Let's let's first remove all the numbers which are not the factors of m from A. This can be the first part. Let's first solve a simpler problem. Does not contain any number which is has power more than 1 over there. So like we can write m equal to p1, p2, p3, and so on, pk. All the powers are distinct. So for example, 6 equal to 2 into 3 is valid number, but 12, which is 2 to the power 2 into 3, is not a valid number. Let's try to solve this problem for the simpler numbers like this, where each power of prime, like for each prime, the power is only 1. And if we can solve it, like we can generalize this idea to solve it on the other part. Now, like the way to solve it would be like we can maintain everything as a mask here. Like if there are k numbers, then we can write the number as a mask from 0 to 2 to the power k open interval here. And like once we know like which mask are these, like we can first find for each mask how many numbers are divisible by it. Like basically, like we look at all the factors, like let's say we have taken 15, 2 into 3 into 5, which would be around 30. Then for each factor of this 2, 3, 1, 2, 3, 5, 6, 10, 15, 30, 1, 2, 3, 4, 5, 6, 7, 8. Like these are the factors. For each number we count like how many factors are there. So like if my numbers are, let's say 1, 2, 15, 6, then number of numbers which divide 1 is 1. Number of numbers which divide 2 is 2. Like these two factors are there. For 3, like only 1 is there. For 5, no, only 1 is there. For 6, 1 and 2 are there. For 10, 1 and 2 are there. For 15, 1 and 15 are there. And for 30, everything divides over there. So like we can first count for each number how many factors are there. And like once we know like the factors, then the number of non-empty subsequences like would be like 2 to the power f minus 1. So like what we can basically write it as here is like the number of non-empty sequences from these 4 number would be 2 to the power 4 minus 1, 15, 2 to the power f minus 1 basically. 2 to the power 2 minus 1, 3, 2 to the power 3, 3, 1, 1, 3, 1. Once we know this, like now we should remove all the multiples from each number to get the exact count. Like the way would be like we start from the 1, like we remove all the numbers which are over here. So for example, like there is only one multiple of 2 smaller than 1. So we subtract 1, we would get 2 here. For 3, like only multiple is 1. So we remove this number 1 minus 1, which would be 0. For 5 also, like 1 minus 1, 0 would be there. For 6, like all of these are multiples here. So we remove 1, 2, 0, which in fact is 3, 0 here. And we can keep doing it. Like the idea would be like inclusion and exclusion type of idea is there. or like I would in fact recommend like this is a really great blog which gives us the insight of how to like the basic idea which I am trying to solve over here. Like same approach works for GCD LCM conclusion and something like yeah. Like the main idea is like for if you look at it as a mask here, when each prime power is only once, then for each mask, count how many numbers are factors of it. This would be the first step. Then whatever be the count, we replace that for each mask, the number of subsequences which can potentially, which has LCM as a factor of this would be like 2 to the power count minus 1. And like the second step earlier we were adding, now we remove all the factors subsequence count. Like I would first show a brute force idea, like then the next ideas were optimizing the same part. Mhm. Weighted FFF. I don't really know why I did got a WA here, but okay, WA was for M equal to 1 case over here. Yeah. So the idea was like I maintain a map vector and like basically I'm trying to add each number and no, like this is not the correct answer to be honest. And like once we know about the mask, like basically first we count like for each mask how many submasks are there. Then we multiply 2 to the power that count minus 1. And then for each mask we subtract like how many submasks were there to get the exact value for that number. And now if we want to look at for the general number, then like we can look at it as like mask as a number in binary. But if we need more prime power, like 2 to the power 3 into 3 to the power 2 into 5 to the power 1 into 7 to the power 1, if the number is like this, instead of looking mask as a binary, we can represent like mask as like these many bits, where the first bit would be between 0 to 3, the next bit would be between 0 to 2, and the next for 5 to the power 1, the bit would be between 0 to 1. For 7 to the power 1, like the bit would be between 0 to 1. And we can do the same idea over here as well. And the idea is we can look at SOS DP as prefix sum over here. Like there are two ways to maintain like counting sum of submask. Like the idea is like we can do each dimension prefix sums over here. Okay, can I get some programming advices from you randomly came across your stream? Like in short, like you can probably join the Discord server, like the link is in the description. There I have a channel like roadmap to RAD in 2 minutes. So there I have answered a lot of common questions. If something is not answered, you can ask me on Discord. I would be happy to answer them. And like now we can like there are two ways to do 2D prefix sum loop over there. Like generally few people like write as DP, IJ as like if we have some let's say a 2D matrix V with some numbers are there. and we want a 2D prefix sum where like a L to LR denotes like the prefix sum of all the numbers from the segment L to R. Like sum of all VI just such that 1 is less than I is less than L and 1 is less than J is less than R. Then like some people like to do it using this way. Like they run a 2D for loop. Vij, like the number at that position, sum of all the numbers from I to J minus 1 plus sum of all the numbers from I minus 1 to J. Like basically, if we need the sum of these numbers, then what we need is these numbers, sum of this range, and sum of this range. And now you can see like this range has been counted twice. So we subtract this range again here. So few people run a loop like this, A I minus 1 and B J minus 1. Like this can be one way, but there is one other alternative way to do this prefix sum as well. The idea is would be like we do it for each row by row over there. For I equal to 1 to n, for j equal to 1 to m. Like we first initialize aij equal to vij, init. Then we write aij plus equal to ai minus 1 j. And like once this loop ends, like you can see like each L2R will contain sum of all the elements in that column there. So like once this loop ends, like this cell will contain sum of all of these numbers. This cell will contain sum of all of these numbers. And this cell will contain like this cell will contain sum of all of these numbers. And now like to get the other part, we can run one more for loop here. For I equal to 1 to n, for j equal to 1 to m, a I j plus equal to a I j minus 1. Like two-step process instead of trying to do inclusion exclusion at same point of time. Now like once now if you pick this number, like you will notice like now taking prefix sum for this cell will give me like this cell, for this cell like the prefix sum would give me all of these numbers. And if you pick this cell, like after the first loop, like after the first loop, like all the cells in this row would be sum of these. And after the second loop, like all the cells, like the last cell will contain sum of all the numbers. This cell will contain sum of all the numbers. This cell will in fact contain sum of all these numbers. And my idea was to run multiple prefix sums like this to get like sum of all the submask first, and then when I want to subtract sum of submask, I did the reverse of this prefix sum idea over here to get over there. And then there were some different ways because I cannot maintain this heavy tuple, so I tried to use this as a product or something like that. This was the main idea I had. Like I will probably go through like my code as well. Like first I used a character library to find prime factorization of each number, how many times a particular power is used. So like that was a black box for me. And like after let's say this for loop, for each prime number I knew what is the power of it in the given number m over there. So like I did not like I directly use the character library, so I don't really know like what all it's some using some polar row to find one factor price prime etc over there. So like because the number is up to 2 to the 1 to 10 to the power 16, like the native for loop of running all the numbers from 1 to 10 to the power 8 might not work there. So like if the number was 1, I simply counted the number of ones in the segment and I simply added it. Now the idea was for each prime factor, like just like I was running multiple for loops for each dimension, we can treat each prime as a dimension over here, similar to we are treating it as a mask. For each time, like generate all the numbers over there which does not include that prime number. Like this was probably a recursive code. And for each number, like take a prefix sum on that power by increasing all the numbers into p over there. Like that was the first loop. Like after I was done with this idea, like my dp1 contains like how many, for each number how many factors are there in my given number. So now I came up with a dp2 idea which would be 2 to the power into like how many factors minus 1. So like these are the potential number of sequences which have LCM, which is a factor of x dot x I had over there. And then I did the reverse part again over here. Like I went for each prime as a dimension. Like first, if you look at it, the first part was prefix, finding this prefix sum. The second idea is recovering each number if I know the prefix sum for each number over here. And that for that I can do like the similar algorithm. Like if I want to get the numbers again, like let's say I already know the prefix sum, I want the original number back. Then the way to do over here, like the loop generally looks like this. Like basically, if you know the prefix sum and if you want to get the original number, you can, for each number, you can subtract the larger minus the smaller number to get all the ranges. And you in fact start from reverse as well. For I equal to n to 1, for j equal to m to 1, for each number, like re- remove the just smaller number over here. For j equal to n to 1, for I equal to 1 to n. If I run a loop like this, like if a is the prefix sum, after the completion of both the iterations, a would in fact contain the original number whose prefix sum was my given number. And like the similar logic I used to find, like given, like if I know the mask, how do I subtract the smaller number over there? I would say like it was more on an implementation side rather than, like I would be interested in knowing like what other people's did. Like this was the first approach that came to my mind and I went ahead with it. And like everything else was generating, like because I cannot explicitly maintain tuple, I try to maintain it as a product and some variable and left and right over there. Like I will probably go for G as well. Like G in fact like was pretty similar to one of the problem I solved before. So like in fact I used the same idea for my summation here. Palindrome construction. A sequence of positive integer t t1 to m of length n is a palindrome if and only if ti equal to t, like it's a standard palindrome definition. You are given a sequence of non-negative integers a1 to an of length n. Determine if there is a sequence of positive integer s1 to sn of length n that satisfies the following condition, and if it exists, find the lexicographically smaller subsequence. Let's ignore the lexicographically smaller part for now. Like for each I, like we have given some integers, some range L to R should be a palindrome, and like the number just before it should not be a palindrome. Let's first forget this constraint as well. Like the first problem, let's try to solve it is, let's assume we are given some ranges L to R. Like let's say we have been given some L1, R1 ranges. And if we want, okay, good luck, Naman. Like first I try to find like what all characters can be equal over here. Like let's say 1, 2, 3, 4. up to NIF. Like if I want L1 to R1 to be a palindrome, then SL1 should be equal to SR1. SL1 plus 1 should be equal to SR1 minus 1. SL1 plus 2 should be equal to SR1 minus 2, and so on. Similarly, if I try to merge it using DSU, then at the end of the day, like I would have each, if two indexes are in same connected component, it means that they should be in the same segment there to begin with. And once I am done with merging all the segments, to ensure this constraint, like this is not a palindrome, I can simply check like L1, Li minus 1 and Ri plus 1 are in same connected component or not. If it turns out to be in same connected component, I print no, because we have some other sequence which says like this should be the same numbers here. Like this would be the first brute force idea we should have on this problem. Like let's in fact first ignore like that was the first part I did. And the next part I did was like, instead of like, if you see like here we have to subtract indexes over here. The idea I did was like, instead of maintaining n elements as a DSU of n elements, we can also maintain a DSU of 2n elements. And we can say that the ith element from starting, like we can first merge 2n minus I minus 1 over here. So basically like each index 1 for the front, and like if I try to do reverse part, or n minus 1, I merge it with n segment here. And j here gets merged with 2n minus j minus 1 over here. Like if I maintain a segment tree, like now there would be n different component, and one component would be there for each index over there. Then instead of merging these segments, what I did was like, I can also merge it with like the other segment I had, 2n minus 1 minus r1, and like this one like would become s2n minus 1 minus r1 minus 1, which would in fact be s of 2n minus r1. This one would be s of 2n minus 1 minus r1. Or like let's just assume zero based indexing to keep our life easy. Or like let's probably keep it as it is. So like now instead of doing it the way like this, I start with L1, and like let's say I have S1 which is 2n minus 1 minus R1. So I may make not as, probably let me pick some other number. Like the main idea is, if I have this as the main sequence of S0, S1 up to Sn minus 1, and like if this is my other part, Sn minus 1, Sn minus 2, so on, S1, S0, then earlier I was trying to merge elements from here in the same component. Instead of going it via this route, what I am trying to do is like, I first merge all the numbers here like this. And now I pick the L corresponding here. And I also try to find the index corresponding to R here, which would be 2n minus R. Now I directly merge these two elements. Now I pick the next elements here. And I pick these two elements again here. And like the same, like instead of now I am subtracting here, I am increasing the indexes here. And like this was the first brute force idea I had. And like we can probably like, I would try to implement this idea once and then I will say the final optimization I did. And like I will probably recovering the original sequence, I will leave it as an homework. I will probably simply explain how to print yes and no. I have an Atcoder DSU of length 2n. I have merged each element with the corresponding pair first. Now I have this function which says L2R should be a palindrome. So I start with U as the first number and N as like the number in the second part over here. And then I take all the segments again. If in fact L minus 1 and R plus 1 ends up in the same connected component, I print no, otherwise I print yes. Like this algorithm will in fact give me TLE, but like this was the first optimization we had. Like W is because like I haven't printed the smallest numbers yet. And the next part was like instead of maintaining only one DSU and iterating on all the loops, or yeah, like we can in fact do something for like how we do maintain sparse table. We maintain log and DSUs. Like in the ith DSU, if L and R in same connected component, it means like SL is equal to SR, SL plus 1 is equal to SR plus 1, so on until SL plus 2 to the power I minus 1 is equal to SR plus 2 to the power I minus 1. And if we maintain log and DSUs like this, like DSU 0 will denote all the correct pairs, and like we can do heavy lifting over here and like the visited part like this on this part. So like when we want to merge a segment, let's say L to R of length 232, like SL equal to SR and so on, SL plus 31 to SR plus 31. Like or like U or V, whatever we say. Then we first check in like the DSU, fifth DSU. If L and R in same connected component, we do nothing, return. Otherwise we merge them and we recursively solve for like SL to L plus 15 and SR to 1 to 15, and as L plus 16 to as R plus 16. Like we now solve it into two different more parts over there, and try to make connections in the fourth DSU as well, and so on. We can keep going this way. And like that was like, if we maintain log and DSUs like this, then we would be able to do it faster. And it's a bit of kind of like the segment tree we had. Like I take the original length, I split it into some 2 to the power I powers over here. Like this is u, this is v. This merge seg2 says like merge all the power starting indexes of 2 to the power j, which starts from u and one side and starts from v on the other side. And then I make a jump over here to get the next power of 2 over here. Now, if I already reached the -1, then I don't have to do anything. If in the pith's DSU, if L and R in same connected component, then I know like everything would be fine over here and I can simply return it. Otherwise, I merge those two indexes and the pith segment tree. I find the new length, half of both the lengths, and I go for P minus 1 segment tree to merge from L to R of length by 2 and L plus length and R plus length, and try it again and keep doing it. So like once you are done with this, like you can take the original rows and see like if L minus 1 and R plus 1 is in same connected component, print no, otherwise print yes. Once you are done with it, like now you know like each connected component should have same number over there. And like to get lexicographically minimum, you can try out like greedily try to pick number for each connected component such that it does not violate the condition for L minus 1 and R over there, which you can probably keep it in a graph, all the numbers like this. Any questions or anything over there? Like the main idea was to maintain like log and DSUs over here and like merge it in such a way that instead of moving two indexes right, you iterate both the indexes forward over there. And like this was the solution. Like I definitely knew how to solve it because like I had solved one problem before in the past, which essentially uses the same idea. So like it would be good exercise to try to solve this problem as well. Like I can read out the problem statement over here. The solution is pretty much same. Michael is the manager of barely known office, and inside his office there is a locker with money to pay to the employees. Unfortunately, Michael forgot the password of the locker. It is now Dwight's responsibility to help his boss. The password is a sequence of n digits containing only zeros and one, and Michael remembers the value at some positions of the sequence, but not the whole password. Michael also remembers m intervals of password that are palindrome. His mind memorizes palindrome for some reason. An interval, this is palindrome definition. Now Dwight wants to know how hard it would be to record whole password. You can help Dwight by calculating the number of possible passwords that follow that Michael remembers. Since the answer is very large, outputted modulo this one. So here the idea was like we maintain like similar log and segment trees, and we try to merge all the connected components using those parts. And if at last we look at each connected component, if there is a digit with 0 in it and there is a digit with 1 in it, then the answer is directly yes. If only 0 or 1 is there, then we know there is only one way to assign digit for that connected component. Or if all the numbers are question marks there, then there would be two ways to assign those connected components. So we can maintain answer as 2 to the power that, and overall we would need the product there. So like this in fact was a really good problem to solve. Like I don't think there is an official editorial for it, but the exact same idea would work here. Like I think I rushed a bit faster on FNG. So if there are any questions or any confusion, you can join the Discord server, and I would try to explain it in the simplified form over again there. And I would say like I would try to mostly say the critical ideas for FNG instead of exact implementation or exact solution for each of the problems. If there are any questions related to Atcoder or anything else, I would be happy to answer them. Otherwise, I would call it a day. If there are no questions, thanks a lot everyone for joining today. Like I will paste this problems link in the comment so like you can refer it. Okay.